Okay, welcome to week 15, episode 25. Let me just update on the announcements. There are a couple changes. Oh, hi, Ziyao and Jim. Hi, Jason. Yeah, so there are a few changes here, there. So know that for this week, there are more quizzes to do. But no worries, quiz 39, you don't have to type up anything, but it's kind of necessary. I just added this quiz this morning to make sure that you get the feeling of doing distance vector routing. Okay. So in the end, we now have many quiz to complete for week 15, but you guys are doing very well. There are 3 more quizzes today, but they are all very straightforward. PA9, the last PA, is during end of the week as well. Next week, I decided to break the last quiz into 2 parts so that I hope that the cognitive load is a little bit lighter. Since that we're doing this, YouTube live, much less interactive way of lecturing. And so these are the changes. And TA finished grading exam 3. Please excuse us for the delay because the TA and I both have some deadlines we're trying to make. But note, although the raw scores started a little bit lower than exam 2, you see that the content gets a little bit deeper as the chapter goes. It doesn't sound like it's all that hard, but as we are testing you see also, okay, there could be some misconceptions. There could be also that from Poly, it sounded that it's easy, but as you're working on answering, it's still a little bit challenging. And no worry, you'll be the score you'll be considering for the final semester grade is this raw score plus 20.62 points. So that's so that is saying that the highest score is actually close to 90 and maybe slightly above 90. And I do know that the lowest score is about 30 something. So although a little bit lower than 60, but it's probably very close to 60. Okay. Yeah, I know. There's exam number 4 still coming. But I would say that take it easy. Use it as a way to check for yourself whether you're picking things up really well. And the flow of today is like this. So I decided to add 2 more quizzes because in the end of Tuesday, I see that you guys are somewhat curious. I do see that there are some answers for quiz 37 being very interesting. So I kind of expanded a little bit more. So that's now go on to the quiz. This is quiz 37. So the setting was that you need to pretend that yourself is X. And you need to decide based on what your neighbor have told you. So Y there, neighbor number 1 tells the cost to your destination W is 2. So this is 2. And Z here tells from him to W distance is 10. So comparing 17 to 2, to 4 together. So many of you chooses to send data through Y, and hopefully Y will be able to forward to W in shorter amount of time or lower amount of cost. Okay, but there was a very interesting solution there. I think it was from Johnny. Johnny Team 3, if I recall correctly. So he was saying this. This is 2, right? And this is 10. So what is the best way? Obviously, is still this. But I think he saw something. From Z to W. Okay, the cost is 10. But X here could do this. Send to Y and then Z. And together, the total cost is what? 13. This will be still shorter than sending data directly to Z and then 10 to W. You see? That gives me an idea for another quiz. Quiz 30A is this. Now, let's change the setting a little bit. What if Y to W is 10 and Z to W is 2? Now your X, what would you choose? Do you forward it to Y or do you forward the data to Z? Now this gets interesting, isn't it? This, on the first look, its total cost is going to be 9, 7 plus 2. Going this way, total cost 12. But is either of these the shortest path? So if you are X, how would you forward data to Y or to Z? Sorry. So let's see. Alright, so Jingyuan and Shiwei and Yuanxiang, you guys chooses to go with Y. Interesting. Why? So you say you ask, you send to Y and tell Y to forward the data to Z. Okay. You not only chooses to forward data to Y, and you instruct Y in the meantime to send data to Z instead of the way you report it, okay? Instead of the way Y reported. Because if you notice the link between Y and Z, the cost is only 1. And we now see from Z to W is only 2, right? Obviously, Y, hey, you, Y there? Excuse me. Why there? Hey, your shortest cost to W should be what? 3, and yet you tell me it's 10. Okay, so no. Y, you take this other way, send data to Z. Z knows a better way that you don't know. Very good. I'll choose Z because the total pass through Z is shorter. Good. So James actually take the way like we did in quiz 37. Double Jelly says pass to Y next since Y can act. Yeah, okay. Yeah, so James was saying that we are not sure that X can tell Y good consideration, right? It really depends on the routing protocol and how much we can really instruct the neighboring routers to do. If this is SDN, where there's like a super being, right? A remote agent there overlooking everything, then definitely. But if this is traditional routing, right? Every router is doing its own computation internally, then maybe it's not that easy. Okay, I think this is a very careful consideration. Very good. Okay, Jingyuan definitely very smart. Same for Double Jelly. Guangzhao send to Z because sending to Z the total cost is 9. If we choose to send to Y, maybe Y don't know all that well about Z exactly, right? So Guangzhou here is having some reservation as well, much like Team 8, James is thinking. CI here on behalf of Team 6, pass to Y and go X, Y, Z and then W. Yeah, this is indeed the shortest pass, isn't it? And Wei Yao here, if we consider greedy, yes, definitely pass it to Z. But as time passes, Y may find a shorter way to pass it to Z. Well, that makes sense as well. Okay. So for now, we know the best is Z. Okay, even though we can look at the topology and see that the cost between Y, Z is very, very short. But Y might eventually learn the best way, and at that time, then we forward the message to Y. Okay, so Wei Yao probably have already previewed the slides already. Yiting, I would choose Y, ensure the message will be passed on to the port to Z. Okay, so you enforce this condition, right? Yeah, so it makes sense. Why won't Y tell? Exactly, isn't it? Why won't Y tell? This is a very good question to ask, obviously. Okay, very good. You've got it, pretty much. Hong Xuan here on behalf of Team 1, you choose Z because, yeah, you don't know the causes between, I see, between X and Y. Do you mean Y, Z and Y? You probably meant Z and Y. This is a very good point, Hong Xuan. Yeah, because in distance vector, I tell my neighbor, hey, when I break open distance vector routing, I say that in link state routing, right, the Dijkstra routing, before the algorithm can run, you need to have the graph, the entire graph. And to store that graph, that's a lot of memory consumption. And we thought that, hey, the reason we need to talk about distance vector is so that we don't need to store that global graph. We don't need to store all that much, right? So the point is so that we don't have to know the cost between, yeah, there you go, the cost between Z and Y. Very good, Hongxuan here. Pei Yu, choose Z for now because X might not. Yeah, for the time being, right? And if we cannot control whether Y will be able to make the right choice to pass it to Z and then shortest pass to W. Jin Xiang here. With Yuze, we choose to pass to Z since YZW is not insured. Very good. Okay. Yeah, I think you guys now beginning to get this better sense of distance vector. And some of you say, hey, you're not quite certain if the link between Y and Z there is an information that you know already at the perspective of router X. Okay. Yeah, even if you know, you have no control whether Y is gonna, really send data to Z. Because each of these router in traditional routing is working independently. Okay, Kevin here chooses Z. All right. Same for Samuel. But Samuel sent to Y, thinking that the shortest way. Wei Shen is choosing to go with Y. Great. Okay. So either way, as long as you can argue for it, it's fine. Now we come back to another quiz. Now this is a new quiz, which is to demonstrate another point here. So let me go down to the next, oopsie. Let me go down to the next quiz. So quiz 39 reads this. So this is a quiz that you get a better idea of what perspective and perception mean. When you are standing at a certain perspective, then you have also a certain perception of how things are. Okay. This is a picture you see, and probably not surprising to see. So there's a gigantic animal in the middle. Can you tell me what it is? Yeah, for this quiz, you guys don't need to type anything up on Slack. You automatically get the score because it's just too simple. Okay, but I do need you to think. Okay, feel free to type up on YouTube chat. Okay, what is this? Trivial, isn't it? But why? You see, if we have some 6 blindfolded people here trying to touch this animal, you see, depending on where they are touching the animal, they actually say different things. Their perception is different. Right? So this guy here at the top sees, oh, it's a fan, touching the ear, right, of elephant. Yeah, exactly, Jingyun. And this guy here says it's a rope. This guy says it's a wall. This is a tree trunk. And, oh, this is a snake or maybe a pipeline. Oh, and touching the musk, that will be maybe a spear. So from different perspective, you perceive things differently. Okay, so I guess that explains a little bit why router X there. Okay, perceive limitedly without the knowledge of the cause of link y and z. In distance vector, we actually choose z, right? Because the sum is lower than the sum of going to y and then directly to w. So we are limited by the perspective. The routers, okay, are limited by the information they have received. And there's another point to make. So for Q1, animal abuse, okay. Sure. That's definitely very abusive. Hey, double jelly. Okay, now you screw my quiz. Okay, so quiz 39 for Q2. Okay, so I'm asking you to guess what this is. Okay, but double jelly, no worry, because you see on the channel that all the hints. But now, think about this. We have a bunch of these testers, and first tester says this. It's a drink. At this point, can you guess what the subject is? Okay, so this question mark box here represents the subject I need you guys to guess. 爱玉, okay, 爱玉 works. Okay, so it's a drink. Okay, but at this point, are you very sure what it is? No, right? So you can only make the best decision you can. What about having, another time point later, you get another hint? Cold. Oh, it's cold beverage. Oh, then it narrows down, right, on the choices. But still, there could be multiple choices. Answer will definitely be less than optimum. So shortest path is optimal. But then tester number 3 and 4 and 5 says this. Oh, it's sweet, and it's soft, and it's chewy. Okay, it's okay, double jelly. It is meant to be simple. Oh, smoothie, yeah, it's a little bit chewy as well, right? You chewed on the ice flakes. Good. 香蕉牛奶, yeah, there could still be some, grinded banana paste there, and you chew on it as well. Okay, fruit juice, definitely. Very interesting. But hey, very close to the shortest distance. So I mean, if I add more clues, then obviously it will take you closer. So the answer I had in mind, 斯乐冰仙草, sure, is this. Okay, wait. Yeah, so what I had in mind is bubble tea. Yeah. Chewy. But I guess I think 偶饮, right? But I don't know 偶饮, how does that spell into English? aloe juice. Yeah, and I think Japanese like to have these cognac, right? It's also chewy. So cold, soft, sweet drink and chewy composite. Okay, sure, Jason. That's a very good answer, by the way. Very correct. All right, so let's now go to quiz 39 channel because it's more to demonstrate that distance vector is also something that works in iterations, much like how these testers, okay, everyone after drinking revealing a little bit more, okay, of what they know. And router X here, after collecting data iteratively, can come to better idea of how to send data. And hopefully in the end, it's the optimum, okay? So let's go on to learn about distance vector routing, the algorithm. My apologies, there are notations again. So with these notations, it gets a little bit harder to, oh, Taro, good, thank you, James. It gets a little bit harder to understand, but try to follow, okay? So math is something that does require a little bit patience. So for the next 10-20 minutes, 可不可白玉? Oh, how do you know? I actually like 可不可 bubble tea very, very well. Oh, okay. So yeah, so let's go to the first video. Okay, pay attention. It's about 10 minutes, slightly longer than 10 minutes. Let's try to pick this up, okay?
That should give you a rough sense how a router discovers a route without seeing the entire network topology. That is asking the neighbors to help. So neighbors will be reporting how they know about the destination. Now you know the neighbor's cost to the destination, and you know the cost for you to reach each of your neighbor. So that be X, and the cost from the neighbor to destination Y. You can calculate the sum of X and Y. If the value here is not infinity, you've discovered a route to the destination. But in order to discover the route that is the best to the destination, then you will need to check through all neighbors. Okay, for each neighbor, you find the cost to each of these neighbors. And you find out from that particular neighbor the cost to the destination. And you sum up, okay, X and Y for that particular neighbor. So you pick I such that Xi plus Yi is the lowest. There, you discover the best route, the shortest path. And I there is the next hop that leads to the shortest path to the destination. And you see right on the slide that what I was describing is exactly how distance vector algorithm works. So we define the term here. dxy is the cost, okay, of the shortest path to go from x to y. And so what we're calculating here is the minimum cost to go from x to y, or to discover the shortest path from x to y. The way to do it is to go over all the v's. Okay, v's are the neighbors of the source. For each v, we calculate the cost to go from the source to the neighbor, plus the cost from the neighbor to the destination. So the sum here is the cost to go from the source to the destination through a particular neighbor v. So all we need to do is just to go over all the neighbors and calculate the sum for each neighbor and pick the neighbor that gives us the minimum value. And that minimum value is the minimum cost, okay, from x to y. And that v there is the next hop along the shortest path to the destination. So by doing this calculation here, we discover the shortest path. We discover the minimum cost. And this equation here is better known as the Bellman-4 equation, because this algorithm implemented in distance vector routing is devised by these two great guys. Let's try to exercise the Bellman-4 equation using an example. And let's calculate the shortest path from U to Z. Right? The first thing to do is, hey, we need to have the neighbors, right, reporting, okay, how they know about the destination. So use neighbor including V, W, and X. So V will need to report the distance from V to Z, and that is the entry here. X will have to report the shortest distance from X to Z. Same for W to report the shortest distance from W to Z. And then we can begin, okay, doing the calculation. So we'll be going through all three neighbors one by one. So let's take the first neighbor V. Okay, so link cost from the source to V is 2. And dVz is 5. So we have 2 plus 5 here. Okay. From U to Z through V, the cost is 7. Second neighbor, X. So this is the second one. Link cost, okay, from the source to X, 1. And dxz reported as 3. So this is 4 here. Wow, nice. Third neighbor, W. Link cost is 5. And dwz, 3. So together, 8. So obviously, 4 is the minimum value. This is the minimum cost from U to Z. And you know what? X is the neighbor that gives you the minimum cost. Therefore, X is the next hop leading to the shortest path. So here, X here, achieving the minimum is the next hop in the shortest path. And that is also, okay, the link pointing to X is the link interface to insert in the forwarding table for destination Z. So that was the Bellman-Ford equation, which captures nicely how one discovered the shortest path, the minimum cost to go from the source to the destination. But you see also in the previous example, right? Calculation of the Bellman-Ford is actually based on these information. Cij, okay, the link cost from the source to each of the neighbors, and these, the shortest distance from each of the neighbors to the final destination. All right. That is also saying the distance vector algorithm as a whole contains the Bellman-Ford algorithm. But before the Bellman-Ford can be calculated, each node will also need to collect these information. Now, this is actually configured in from the network admin when the network is established. Now, this actually relies on the neighbors, okay, sending their routing information to the node. Okay, so next, what I'll be talking about is to go over the entire distance vector routing algorithm, covering both the message passing part as well as the Bellman-Ford part. Now, before I talk about the entire distance vector routing algorithm, let me introduce just one more notation. dxy is the shortest distance from x to y. This is not new. The new one is here. A node is going to maintain the shortest distance from itself to every possible destination existing in the network. So, capital N here is the set of the nodes in the network. So we do have multiple values of these dxy, okay? Because there are multiple values of these y's. So each of these values is the distance, the shortest distance to a destination in the network. Therefore, we call this a distance vector. It's denoted as capital D. Okay? Now, because this is a distance vector for node x, therefore it's called the dx. Good. So the distance vector routing algorithm, the goal is to derive dx, okay, for each node x. Great. And before we could calculate dx, okay, the node here needs to have two pieces of information. Okay, according to the Bellman-Ford equation, we need to know the link cost from the node to each of the neighbors. So CXVs. Now, in order to have the shortest distance from each of the neighbors to a particular destination, yes, we need to also know, okay, the neighbor's distance vectors. So for each v, no x here also maintain dv. And now the algorithm of distance vector. You see here, a key idea is it works in two phases. First of all, each node sends its own distance vector to the neighbors. So this is the message passing phase. And then two. Yeah, when the node receives the distance vectors from all the neighbors, yeah, Bellman-4 equation calculation begins. And as a result, okay, the node x there discover its own distance vector. And we could loop back. Okay, this node here then will pass the dx to the neighbors. That is the general idea of distance vector routing algorithm. The Bellman-4 equation, now this is the Bellman-4 equation. Okay, know that when x receives all these dv's from the neighbors, dx is not just one value to one particular destination. So this Bellman-4 equation is going to be called, again, these many times, so that we derive the shortest distance to each of the possible destinations in the network, n. Alright. Yeah, final note here. Under minor natural condition, the shortest distance from x to y, at the beginning, it might be really bad. But as time goes by, it's going to converge to the actual least cost. So minor natural conditions means that, yeah, for normal internet operation, this is going to hold true. To be more precise, this is distance vector routing algorithm, and it's depicted such that it looks like it's working in cycles. So each router in the network operates such a cycle. First, it's going to wait for one of these two events. Very common is that you receive a distance vector from the neighbor. Occasionally, this router here might detect there's a link cost change among these links to the neighboring routers, because these two events might affect the result of the Bellman-4 calculation. So when these two events occur, we trigger Bellman-4 calculation to begin. As a result, we get a new distance vector. Now, if the distance to any of the destination has changed, that means, better route discovered, shorter distance discovered. Then we tell to the neighbors, because the neighbors might also benefit from the good news, benefit from the discovery. Right? So you see, distance vector routing algorithm working this way, it's iterative, meaning it works in cycle. In each cycle, it can only be triggered by two kinds of events, link cost change and DV update messages arriving at the router. It's also distributed because one can calculate and discover a better route and pass it to another node. So each node notifies the neighbors of a better route, and the neighbors then calculates even better route and notifies the neighbors. So in the end, they converge to the shortest path, but the effort is actually shared, distributed, and contributed by all the routers in the network.
All right, so interesting, isn't it? Yeah, so let's look at an example so it's a little bit more concrete, all right?
Okay, example time. In order to make sure that you understand this thing clearly, let's use a concrete example. So the example this time, very simple, only 3 nodes, x, y, z, and they are fully connected. Oh, by the way, we have not yet talked about initialization of the distance vectors. In node x, the distance vector of x is initialized this way. For destination x, well, it's itself, therefore, distance 0, it does not cost anything to transfer data from x to x. To go from x to y, let's initialize it to the link cost of xy if they are adjacent to each other. So 2 here. xz, so xz, they're adjacent, therefore we use the link cost between xz. Similarly, you do the same thing to initialize dy for no y, dz for no z. Now, hey, in no x, it maintains all neighbors' distance vector, alright, but at the initialization phase, no x did not receive anything from y nor from z yet. So dy and dz, these two vectors, are left null. Okay, so I'm just using the sign of infinity there, okay, to represent their null. Similarly, for dx and dz in no y, and so on and so forth. So this is how you initialize, okay, the initial distance vector table, which is composed of 3 vectors. Okay. You maintain your own vector, you maintain also the neighbor's vector. Now, once, okay, the vectors are initialized, each router will what? Okay, notify the neighbors. So this vector here will be sent from x to all the neighbors, y and z. Similarly, no y is going to send its initial table to x and z. And similarly, z sent to y and x. All right. And that's why, okay, in the next cycle, no x here in the table, it's going to see dy from no y, dz here from no z. Now, with neighbors distance vector in place, now we can begin to calculate the dx. So what is the value of dxy? What is the value of dxz? Now let's start from calculating dxy. Right? So the Bellman-Ford equation says we try through all the neighbors, okay, of the source. X is right here, the source, 2 neighbors, y and z. So yeah, we do have 2 entries here. Okay, one is assuming neighbor being y. Second, using neighbor z. So, okay, for the first sum, we use the link cost from the source to first neighbor, and then adding the shortest distance from the neighbor to the destination. Now, in this case, neighbor happens to be the destination, so this is 0, okay, as dy y says 0. Link cost xy, 2. So 2 here. Now, for the second neighbor, z. Link cost of xz, 7. So 7 right here. Shortest distance from neighbor z to destination y. Okay, then we need to look up the table. From z to y. Right here, it says 1. So 7 plus 1. This is 8. And this is 2 only. Therefore, y here wins. Okay, y is the next hub router, okay, to y. So therefore, we write 2 right here, okay, for x, y. And now we derive dxz. Okay, so from x to z. Again, from the same source, 2 possible neighbors. One is y, the other is z. Link cost from x to y, 2. So 2 right here. Shortest distance from y to z, we'll have to look up the y row here to z. So the distance vector from the neighbor y suggests it should be 1. That's what we are seeing here. Now for the second neighbor z, link cost from x to z, 7. So 7 here. Shortest distance from neighbor z to z, trivial. And yeah, it should be 0 here in the table. So this is 7 and this is 3. Therefore, y wins again. to go from x to z, take this path. And we can add 3 back to the distance vector of x. And what do we do next? Yeah, now x here acquired the new distance vector. It's going to what? Send it to all the neighbors. Okay. So this is the first cycle, calculating the dx, okay, from the x's point of view. Similarly, no y there is going to be calculating the dy. No z there is going to be calculating the dz because it's receiving dx and dy.
Alright, so guess what? Next step is let's try calculating dz. Okay, develop the table in no z at the first iteration, which is this thing. So we just developed this table, right? Now let's try develop this table, in particular dz here. Oh wow, okay, that was fast. Let's see. Three and one. All right, great, good, very good. Oh, okay. Yeah, I think Johnny and Jingxiang's answer are a little bit more detailed. That's great. So you guys can see clearly. Wow, okay, look at this, Jingxiang and Johnny. So definitely, right? dzx, z is definitely going to be here. Oh, okay. And x is going to be here. And so neighbor y, right? And then this is through neighbor x. So link zy causes 1. The yx, we'll have to look up the table. Yx, the first entry of the second row, right? So that must be 2. Okay, very good. Yeah, you guys got it. Comparing 7 and 3, comparing 9 and 1. Very good. Good. I see that you guys are picking it up quite okay. The last video is actually to walk through the same thing. Let's try to calculate the distance vector of z together. So you see, it will be the shortest distance from z to every possible destination in the network. And in the network, it's very small. Starting from z, there are only 2 possible destinations, x and y. So we just need to calculate dzx and dzy. Now let's calculate dzx first. According to Bellman-Ford equation, okay, so what we do is to try to find out, okay, through all these neighbors connected to the source, okay, which one leads us to the shortest path to the destination x. Now, in this network, we do have 2 neighbors, okay, connected to z. So let's try the first neighbor first, which is z. So we'll be using the link cost from the source to the neighbor. So link cost from source to neighbor, z to x being 7. And then based on what the neighbor knows, okay, the shortest distance to the destination. In this case, neighbor is x, destination is also x. Now we look up the table. So dx here being known to z, according to that, the x is 0. Now the second entry, the second neighbor is y. And so we'll then take
link cost from z to y, which is 1, and then based on y knows the best to the destination x. So dyx, okay, is the value we need to add link cost zy to. And according to the table, okay, dy says dyx being 2, therefore 1 plus 2. So going through x, we get a pass. The cost is 7. Going through y, we get a pass that the cost is only 3. Therefore, 3 wings. Okay, so you see here, to go from z to x, the shortest path distance is 3. And
I think we get the idea. So we can move on to distance vector. A really strange property here. Bad news, travel slow. Good news, however, travel really fast. Okay, so it's actually a great property, but in case there's bad news, which means if a link suddenly break, if we want to be able to update the forwarding paths to reflect the change, it can be a bit of a headache. Okay, so now let's take a look at this video and see what the
very
problem is.
interesting property with the distance vector routing is this. Whenever there's a good news in the network, it travels really fast. Okay, so when there's a better route, it gets propagated really fast and everyone converge really fast. But if it's bad news, meaning if a route suddenly go bad, okay, it would take a long time for everyone to discover, okay, the route is really bad and we should really be going another way. So let me describe the first case, the good news travel fast case. So recall. Okay, this is the change where the link between x and y is reduced from 4 to 1, so good news. The node is going to detect local link cost change and update the routing information and trigger Bellman forward. If the distance vector changes, then send to the neighbors. So here, link change from 4 to 1. So at time 0, y is going to detect the link cost change and update its dv and inform the neighbors here and here. So next point in time, z here, is going to receive this distance vector from y. Okay, it's going to see, oh, the shortest distance from y to x is now 1. Okay. Therefore, z is going to update the shortest distance to what? 1 plus the cost from going from y to x, which is 1 now, that is 2, which is better. Okay, so z is going to update its own dv and send it out to the neighbors. And y is going to receive z's update. Okay. Z says, okay, the shortest distance to x from me is 2. And y sees that, hey, I do have a direct connection. My shortest distance is already 1, right? Your shortest distance to x is 2, plus the link cost from y to z. This path is not better. Okay, so y there will not discover a new path, okay, a better path to x. Therefore, distance vectors stay the same. Okay, no more message being sent out, okay, back to z. Network converges. Everyone goes to the steady state. The second case is the bad news travel slow. So you see from the scenario, the link cost instead of dropping to 1 now goes up to 60. Super bad news. Of course, x and y here would detect there's a link cost change. But in this scenario, it would take us 44 cycles until the network goes back to the steady state, until they all converge to valid shortest path. Okay. Now, bad news travel slow, meaning routes converging slowly. Okay, that is also referred to as the count to infinity problem. Now let's go to a quiz to see what's going on there. Okay.
Yeah, so we obviously don't have time for that quiz. Therefore, you see next Tuesday, we're gonna open the lecture with the quizzes such as today. Okay. Before you go, there was a really interesting question from Jing Yuan. If there is a change, okay, before the computation is done. For example, hey, Bellman-Ford is in the process of computing the shortest path, okay, based on the perception, the shortest path. But there's another distance vector from one of the neighbors coming in. What do? Well, usually according to the algorithm is that after we are done with this iteration of computation, we distribute the distance vector we know the best, no matter what. And then we go on to process the next message coming in. Okay, so it's still triggered by these receiving distance vector, we compute what we know better, and we distribute our distance vector. Okay, but of course, one can think of a way to optimize, right? Before sending it out, because there's another distance vector coming in, right? We could actually check, right? Before sending our distance vector out to reduce the number of messages, because we can actually integrate two distance vectors before we decided to send the best message out. Yeah, so that would actually reduce also the amount of recomputations that the neighbors will need to do as well. Yeah, so it's a very interesting question, and that's it for today. Join me the last lecture next Tuesday. Okay, so I'm just gonna finish typing up the answer. You guys are free to go. Okay, Jean has a question. How would the node initialize the cost to a node that is not adjacent? Okay. Would each node know the existence of all the nodes in the network? That's a good question, Jean. During initialization, all the node knows is just the direct neighbors, unfortunately. There's no global graph. Yeah, so the cost to the other nodes are just infinite, but you see that when I'm showing the distance vector table, right? So there's distance vector for router X, and there are some other distance vector, but these are the distance vectors X receive from the neighbors Y and Z. Although this topology, this network that we are doing for the quiz has only 3 nodes, but in real world, you can potentially have other nodes where there's no direct connection to X. So X there will then maintain just still 3 vectors in the table. And that's it. Okay, so the size of the table is essentially the number of rows there are is just itself and the number of neighbors. So it's not tracking the entire network, so there are no n rows. Therefore, you don't really need to track, to all the other nodes, the cost is infinite. Okay. So in a way, it's a very good point, Jean, that you brought up, because I kind of, that the way I present initialization process is a little bit misleading. Yeah. So the table there should just, in the initialization, should just have 1 vector for X, and 1 vector for Y, and 1 vector for Z. And those are just so that you see later on we need to develop into the next iteration. You'll see we are expecting the vectors from the neighbors will fill in the infinity. Yeah. Okay, so yeah, let me just clarify, particularly to Jean, and maybe some of you get confused as well. In the initialization phase, in actual distance vector implementation, we just have our own vector, and that's it. And the vector, the size of the vector is exactly to ourself and to the neighbors, and that's all. Okay, that vector size is also limited by how the neighborhood is. Okay, so I'm gonna type up the answer for that here. Again, feel free to go because you're gonna see the answer if you come back later to YouTube video. You'll see also towards the end of the video the answer to the questions. Let's see, there's another question up in the ask us anything. Wasn't the news going around and around? Very good. Is there a timeout for the news? And how do we identify the nodes by IP addresses? Yes. Okay, let me go. Let me just finish the typing up answer for Jingyuan's question. But one can certainly optimize the process by taking subsequent incoming distance vectors into consideration. After finishing multiple rounds of Bellman-Ford, then send just one distance vector out. Okay, yeah. At Jean. To a node that is not adjacent. Yeah. So in a way, we don't know what other nodes there are in the network except for the adjacent nodes. So we do not initialize those link costs, those entries. And part 2 of the question. For part 2 of the question, we eventually, let me see what the question was. Would each node know the existence of all the nodes in the node? No, we don't know. Okay, no. We just don't know. We just know our neighbors, and that's it. Wait, is it? No, I was wrong. Sorry. We learn from the neighbors. Eventually, all the existing nodes in the network. Yeah, we learn these nodes, but from the vectors from the neighbors. Okay, and we include that in our computation. So if there's a neighbor who doesn't know some of the nodes, but we discover now, the next iteration they would discover, oh, there's another node over there. So eventually, everyone learns about the nodes in the world. Now, I understand what the question is. It cannot be like, you cannot declare this table here as an array because you need to know the size, right, of the array. I see where you're going at. Very good. But you can still use like a linked list with index. Okay, so good. It's a little bit tricky, definitely, implementing distance vector. Yeah, obviously it needs to be like that because you don't know how many nodes there are. But of course, you can try to declare like a really large number, then you don't, so that you hope that it covers all the cases. But it's actually a little bit hard to know. Mm. By the way, okay, so I'll see if I can talk about BGP, which is one of the routing mechanisms running on the internet that's using something like distance vector. But it's actually an extended version of distance vector called the path vector. Yeah, but chances high that we might not have enough time to talk about it. You see that that's a routing protocol used for the global internet. The number of destinations we have is still growing. Yeah, so we will have the IP address space limitation issue there. If we implement the distance vector table in a way that it's static, the data structure in a way that it's static. You can also see that it's overly memory consuming as well. Okay, so that was Jean and Jingyuan's question. Let me come back to Samuel's question, which is on Slack. Wouldn't the news go around and around and around? Yeah. It does, but it will stop when we do not discover better information. Because the way we send the distance vector out is when there's something that we need to update, right? If we have nothing to update there. There's no newer information than last time I passed the distance vector out. Router there does not pass the distance vector out. Okay, so it does to some degree. All right, no problem, Jean. But it will stop when we do not discover better information. Okay, so know the second part of DV algorithm. So we update the table and disseminate, but there's a precondition. We update the table, but in case there's no change, no dissemination. Good question, allowing me to clarify that if there's really no change after computation, the distance vector is not disseminated further because it's not better than what the router has informed the neighbor last time, right? I think this is quite intuitive as well. But I understand there could be buggy routers. Buggy, not buddy. Sorry, buggy routers. Hey. Some of them could be newbies to the industry. Get disseminated without checking if there is any change. In this case, it'll be unfortunate. We'll have ghosts, DVs, traveling the internet forever. would not say they are ghost DVs. These misbehaving. Routers will continue to generate unnecessary distance vector to the neighbors. But this will be contained within the subnet of misbehaving routers. As long as it touches a well-behaving router, then it will stop. I hope this addressed the question. Definitely, yeah, you are perfectly right. Yeah. If this is distance vector running locally within a subnet, so the answer is two parts. If DV is used within a subnet where each router is identified by its IP address, yes. But if DV is used at a higher level, between domains, for example, the node is better identified by the prefix. Or AS number, which is something that we're going to talk about. Hopefully, towards the very last part of Tuesday. All right, that's close, and let's go to the end stream.